So we're finally up to the last place where sodium can be reabsorbed in the kidney, and that's the collecting duct. So let's take a close look at that. So the collecting duct is a little more complicated, mainly because there's more than one kind of cell that lines it. So here's one kind, and then here's another, which we'll draw a little smaller. And on this side, maybe we have one, and then the other. Now the two kinds are principal cells, that'll be a principal cell, and intercalated cells. And actually there's two kinds of intercalated cells, there's alpha and beta. But for sodium reabsorption, it's really the principal cell that we care about, and so that's what we're going to talk about in this video. So how do principal cells work? By now you can tell me the first part. It has a sodium-potassium ATPase on the basolateral side. And then on the apical side, what does it have? Well, finally we get a break. On the apical side, it has a simple channel that just allows sodium through. And it has a nice name. It's called an ENaC. And that stands for epithelial sodium channel. So the sodium concentration is very low inside the cell, and that's because of this pump over here, and that causes sodium to diffuse in through the ENaC, and so sodium's path through the cell looks like that. Now what about potassium? Potassium, as usual, needs a way out because you keep pumping it in, and so it can go out through a potassium channel on that side, and it can also go out through a potassium channel on this side. So that means that instead of just kind of going in circles here like potassium was doing in some of the other cells, here some potassium can also actually cross the cell in that direction. So that means that these principal cells can reabsorb sodium and they can excrete potassium. Now we're going to talk about potassium later on and how the body deals with it, but it's a good thing to notice for now. Now a while ago we mentioned that if you have high sodium intake, you want to excrete more sodium. And we mentioned that it's the distal part of the nephron that does that. And in particular, this ENaC channel is really important. The idea is that if you have a very low sodium intake, your body is going to make sure there's a lot of ENaC channels here on this side of the principal cell. And that way sodium has no trouble getting back into your system. Whereas if you have a high sodium intake, you're going to have reduced number of ENaC channels so that you don't reabsorb as much sodium and you can excrete more. But that's just a little bit of a spoiler. We're going to talk about all the mechanisms for how that happens in the future. Now let's move on to the next part of the nephron, which is the distal convoluted tubule, and let's talk about how sodium is reabsorbed there. So as usual, let's draw the inside of the DCT, and here are the cells lining it. And just like with the loop of Henle and the proximal convoluted tubule, what's driving the whole system here is our sodium-potassium ATPase. Now all we need to know is what's the transporter on the apical membrane, and here it's a different one from anything we've seen so far. It's a sodium chloride cotransporter. What drives it to act this way, since it doesn't use any ATP? Well, it's the low concentration of sodium in the cell. So sodium follows this path to get out. Chloride is going to go through a channel on that side. And potassium also needs a way out because it's getting pumped in so much by the ATPase, so it circulates like that. So the thick ascending limb is where you reabsorb most of the sodium in the loop of Henle. So let's look at that in more detail. So let's say this is the inside of the loop of Henle. So filtrate is traveling up that way, and you want to reabsorb sodium across the walls like that. So here too, of course, just like the proximal convoluted tubule, the walls are lined by cells, and once again, they're epithelial cells. And now that we've already gone through reabsorption in the proximal convoluted tubule, the rest is going to be really easy, because here in the loop of Henle, for example, it's the same story. On the basolateral side, you have your sodium-potassium ATPase that is pumping sodium out of the cell back towards systemic circulation and exchanging it for potassium. And that creates a very low sodium concentration in the cell that drives sodium to diffuse across the apical membrane. Now, the only difference with the proximal convoluted tubule is that the transporters here on the apical membrane are different. And for the most part, there's one that you really need to know, and I'll draw it here. It's a cotransporter, meaning it actually transports several things, and what it transports is one sodium as well as one potassium and two chlorides. What's driving this diffusion is the high concentration of sodium out here, and that's what causes it to go in this direction rather than the reverse. So you can see that sodium is going to take this path to get through the apical and then this path to get through the basolateral membrane. But what about potassium and chloride? Well, we're going to have a potassium channel that lets potassium through there and a chloride channel that lets chloride through there. So chloride will take this path and potassium will take this path. And the reason these two will diffuse across the basolateral membrane in that direction is that their concentrations in the cell will be higher than on this side because they keep getting pumped in across the apical side. Now we know how sodium is reabsorbed from the proximal convoluted tubule, so let's move on to the next part, the loop of Henle. And if we're going to do that, this is a good time to admit that we've been drawing the loop of Henle a little less precisely than we could. So let's cut this off and draw it the way it should be drawn. So the loop of Henle actually has three parts. Here is the first part, and then here is the second part, and then finally here is the third part. And this third part leads to the distal convoluted tubule, which goes to the collecting duct. So what are these parts of the loop of Henle? Well, this first part, as you can see, is pretty thin, and urine that comes through here is going down. So therefore, we call this the thin descending limb. So it's the thin descending limb of the loop of Henle. And since I've told you that, you could probably guess the names of these other two sections. This next one is called the thin ascending limb, and this one here is called the thick ascending limb. And if we're talking about sodium reabsorption, it happens mostly here in the thick ascending limb. So for now, we're going to focus on that part, and then later we can come back to why we have this thin descending limb and this thin ascending limb.